We'll talk about shuffling large decks of cards and the Bernoulli Laplace own model. Unfortunately, it turns out that Evita didn't know she's supposed to go for dinner, and she has to catch a train going to Brown University to give another talk. So there's no dinner tonight. But hopefully, maybe next semester, we'll invite her again and she promises to have dinner.
All right. Thank you so much for inviting me. It's a great pleasure to be here with you. So today I'm going to talk about a problem that came to us from cryptographers. So let's see what the problem is, straight to the point. Imagine that you have a deck of 2n cards. You'll see why 2n in a minute. And it's quite big, n is big. Okay? And the question is, how do you shuffle a large deck of cards? So a model that was suggested by these cryptographers was the following. Cut the deck into two piles, each of size n. Okay, so equal piles. Now suddenly you've made your deck. Does this move?
Yes.
Yes.
Yes. You got to push it up really hard.
Yeah.
Okay, so now you have suddenly a smaller deck, and there is some traditional theory on how to shuffle a smaller deck. So for example, what people do is take your deck, cut it at random, and riffle shuffle. That's the usual way that people shuffle. And we know how to do this. So do this many, many times. So now say, shuffle each pile perfectly. Okay, of course we cannot really do perfectly, but for our model we will assume that we can do it perfectly. And independently. Its pile is shuffled independent of the other. Then what you want to do is assemble, bring the one pile on top of the other. And then at the end, now that you have your entire deck all together, cut the top K cards to the bottom. Later, this model will make more sense. Okay? Does it sort of make sense what I'm trying to describe here, what the process is? So let's say this is the way that a casino dealer would shuffle. Okay? So this is not a made-up problem. This is one recommendation. Okay, another way that they do it, which is a really bad way, is that they just throw the deck and they just start doing this. This is really bad, actually. It's not good for you. That's what it means that it is bad. And now, but honestly, we started working in this problem because Dan Bonnet's group from Stanford asked us to solve this. By solve, I mean the question is how many times do we have to do it? How many times do we have to repeat this? Repeat this process for the deck to get shuffled enough. Everything will become rigorous in 5 minutes. Okay? So this is the question that we will be asking today. And to study this problem, we will consider an equivalent problem, the Bernoulli Laplace problem. So I'll bring this up again. Those points should have them next to each other. So now you have two urns. Why two? Because that's how many piles we also have. If I had more piles, something that I'll discuss at the end, I would have more urns. So start with 2 urns. Each one contains n balls. Okay? Let's say that at the beginning I have 2 urns here. Here I start with n red balls. And here I start with n white balls. So there is no distinction among the red balls, and there is no distinction among the white balls. A red ball is different than a white ball. The model suggests now to pick k balls from each urn. And switch them. And then the equivalent question, I guess, is how many times do I need to do this? Sort of gets shuffled again. I will be explaining what shuffled in this case means in a second. Now let's take a look. Why are these things sort of equivalent? So I have 2 n parts. I cut them into 2 piles. Each one has size n. If I shuffle the first one perfectly, that means that I'm identifying all of these cards. They're the same, basically. And when I shuffle the other cards, I'm identifying them, and all of them are the same. So I'll be calling them the red cards, and the white cards. Now, if I'm assembling, and I take the k top things and move it to the bottom, then this also pushes the k top cards of the bottom pile to be moved to the top pile. So there has been some interaction. I moved k things from one pile to the other. And since these were in random order, it didn't really matter how it happened. Okay, so this is how these 2 things are linked together. Okay, so from now on, I'll be focused on this problem. Okay, and this actually turns out that, this turns out to be a famous problem. It has quite some history. So, history lesson before we get into the math. First of all, it was introduced by Daniel Bernoulli. So Daniel Bernoulli has studied a lot of urn models. In particular, the one that I can find in the bibliography is the one where you have 3 urns. Let's say here you have n white balls and red balls at first, and black balls. And what he was doing is that you pick a ball from here and move it to here. Now suddenly you have n plus 1 balls here. So now you pick a ball from here and move it there. And from here you pick a ball from here and move it back here. So it is different from what I'm describing. I'm just saying that this is the type of urn models that he was studying. And the question that he was focusing on was, what is the expected number of white balls in each urn after t steps? So he asked different types of things, but logical things. Laplace actually studied this specific problem for k is equal to 1. So now you have 2 urns, and white balls and red balls. You just pick one and you switch. And he used some differential equation method to actually say what is the distribution of the number of red balls, say on the second urn after these steps. And of course, because back then they didn't really have differential equations, that means that he caused a lot of trouble and people were arguing, is this rigorous, is it not? These are famous fights that mathematicians had many years ago, right? Okay, so now Markov introduced the first Markov chain based on this model. Okay, so and so now I think the paper that I can find, I think, is at 1906. That's when the first Markov chain was introduced, but it is all in Russian, so I asked friends of mine to read it and tell me that it indeed is the correct paper. I cannot tell, so good. So, but back to this problem. Let's make all these statements a little bit more rigorous and mathematical. So, since I only have two urns and two types of colors, all I need to care about is the number of red balls, let's say, in urn 2 at time t. So after t steps, if I know how many red balls I have here, then I have n minus that number white balls in here, and then we can figure out how many balls we have over there as well. So this is why this is what we will be keeping track of. So now I want to define a matrix whose ij entry is the following thing. The probability of starting with I red balls in R2 and having J red balls after one step. Okay, does that make sense? And of course, I want to be taking many, many steps, so I'll be taking the tth power of this matrix, which will be giving me exactly the same thing, but now after t steps. So this is what matrix multiplication will be doing in this case. Okay? The ij entry of the tth power of this guy will be giving the probability of starting at I and moving at j after t steps. And there are all sorts of things that you can ask about this matrix. What are the eigenvalues? Does it have real eigenvalues? Can I use them to say something about shuffling? And although we did do, let me say, the first thing that I should have said here, I'm about to state theorems. Everything that I'm going to say here is joint work with Brown-White. In case I can get right in the theorem, let me say that everything here is joint work with him. And although we did use eigenvalues and eigenvectors to say a few things, this is not what I'm going to be talking about today. So what happens now is, let's fix I. Let's say that I start with 0 red balls on urn 2. Suddenly this is a measure. This is a sequence of measures. What do I mean? Well, if I sum in terms of j, I'll just be getting 1. That means it is a measure. And it's a sequence because t can change. Okay? And I can ask, does this sequence converge or not? So it turns out that this thing will converge as a measure. I'll explain the norm in a second. To this hypergeometric type of measure. So let's put the j back here. So n choose j. This is the measure that this will converge. So what does that mean? It means that the more steps that I start taking, the rows of this matrix will start looking like this measure here. Okay, and this is what it means that I'll be getting shuffled. Like I will start looking like this specific thing. And the question is, how many steps do I need to take to start looking like this guy? Enough. I mean, it doesn't mean that I'll be identical to this. So we're studying this convergence usually with respect to the total variation distance. So this is a half of the L1 norm, so let's write it down. And just a small exercise, it's not too difficult. Since I have a finite space, my space is either I have 0 balls, or 1 ball, or 2 balls, or up to n red balls on urn2. Prove that this is the same as this, taking a subset of 0 to n. And considering this difference and maximizing it over all these subsets. So we will be using these definitions now to prove some things. The question is, so the mathematical formulation of how many times do I need to do this is, if you give me epsilon, I want to find the mixing time, which is, let's say, the minimum t, such that this thing becomes less than epsilon. So this is what I'm trying to find out.
It is also very, very highly concentrated around another theorem.
Yes, this measure, and the variance, the square root of the variance will be root n. So yes, absolutely. So it will take some time. So in particular, this observation will be important for the theorem that I'm about to write. So let me give you one more reference here, which is that for the case of k is equal to 1, Diaconis and Sashahani have proved the following two things. One, that if we take something like n4 log n steps and a little bit more, then the total variation distance is really, really small. Maybe I'm forgetting a 2 here, maybe there is some constant, but I want to say it is exponentially small and we know the constants. And if we take a little bit less, then the total variation distance is really big. Something like this, where they know again what this constant is. It's not. So let me draw this picture so that you guys see what this theorem says. This is a cutoff statement, and this is really in fashion these days in probability to prove and try to understand cutoff. So this means that when I start, so this is time, and this is total variation distance. Okay? So at time 0, you start at 1. You're too far away. And you keep being on 1, and suddenly it drops. That's what cutoff means. So this over here is n4 log n. If I take a few less steps, I'm big, I'm almost 1. If I take a few more steps, then I'm dropping exponentially. In this case, at least exponentially. Okay? So this is the type of theorem we are interested in Markov chains these days, and in particular cutoff. Now what Graham White and I proved It's not quite cut off yet. We have to work on it a little bit harder. But we worked for general K. And the theorem says the following thing. And I'll be trying to prove parts of this theorem today. So, okay, so A, it says that if T is of this form and a little bit more, then the total variation distance is 1. What does this mean? This is a little bit weird and it looks different than the n4th log n. Well, let's say that at least if k is O of n, so if k over n goes to 0, then this basically means that we need something like...
So this is the relation of this? When
It's
k
okay.
equals 1, you get this back?
This is for k is equal to 1. So here you switch just one ball. Here is switching k balls.
So you get exactly this when k equals 1?
No, that's let me tell you. Let me tell you. So because it's a 2.
Oh yeah.
Here it's a 4. And we care about this constant to prove the cutoff. We get the correct order, but we need to play a little bit. So this is something that I'm trying to do now with a collaborator of mine at Princeton.
Oh, so that's a little bit worse. So
It's a little, the upper bound's a little bit worse.
Yeah, but not much. Yeah.
So, but not much. Let me write explicitly. If k is O of n, then this is something like n over 2k log n plus cn over 2k. So this 4 turned into a 2, which is not as good. Okay, so this is something to fix, and we actually read recently a paper about the easing model that treats something similar, and we try to understand this argument and apply it here to see how we could turn this 2 into a 4 and get cut off. Because the lower bound that we get has a 4. So if k is away from n-half, and this statement has to do with your observation that the stationary measure is very concentrated around n-half, then for t is equal to n over 4k log n minus cn over 4k, the total variation distance is big again. So we get the correct constant for the lower bound. And see what happens around n-half, and I'm not going to get very specific over there just because it gets too technical and maybe it's not necessarily as interesting, but if k is close to n-half, maybe distance log n from n-half. By the way, I should have mentioned here that k, we take it to be less or equal than n-half because this is a symmetric model. If k is bigger than n-half, I can play with n minus k and turn it less than 1/2. So this is why here, that's what I'm assuming. For k close to n-half, then we basically need something like constant. Mixing time is something like constant. And this is exactly the observation, because if I change n-half of the balls, then I'm immediately at n-half, and therefore very, very close to the stationary measure. So I don't need to take further steps. Okay? So just saying that I think that today I will concentrate mainly on part A. And if we have some time, I might give a sketch for part B, but I don't think we have time for part C. Part C, as I said, uses the eigenvalues and eigenvectors of this matrix, which turn out to be the dual Hahn polynomials. And so we need to talk a little bit about spherical function theory and representation theory, so I don't want to go towards there. I want to stay to some probabilistic techniques a particular what is called coupling. So, I think I will move here to the. So as you see, this is meant to be an understandable talk, so feel free to interrupt me if there's something I'm not explaining very well. So the technique that we use for part A is coupling, or in fact something a little bit more sensitive than that. We use path coupling. So let's explain this. In fact, let's use the definition of the total variation distance that I care about. So the total variation distance is the maximum of all sets, subsets of 1, 0 through n. Okay, so this is what we were studying. So we know, for example, I chose my process to start from 0. At time 0, I have 0 red balls on R2. Right? That's how I started it. Now I'm going to consider a different chain. Let's call it YT. So here I have the chain XT. And YT, where Y naught will start from something that is chosen according to the stationary measure. So, okay? But this is still a nerd model. So still I can keep on picking K and switching them, picking K and switching them. And I'll be doing the same thing here, picking K and switching them. But I'll try to couple somehow these moves so that eventually these two will meet. I want eventually to have X3 to be equal to YT. And I claim that the first time that this happens will give me a bound to the total variation distance. So I need to couple the moves of the Markov chain. Applying on XTYT so that eventually XT equals YT. I'll become way more specific once I talk about this problem and tell you how to do it. Now, if capital T is the first time XT is equal to YT, then the coupling inequality says that the total variation distance is less or equal to the probability that T hasn't happened yet. And this is what I'm going to be using to bound the total variation distance. And even if this is confusing, don't give up hope. I'm about to show everything on our problem. So it should not be too bad. So what I'm going to do is, okay, I start with my process. So here I have XT. Say at time T, maybe I have three white, four red, and maybe here I have 4 white, 3 red, because remember the number of balls has to be the same. And now I will only consider the YTs that are differing by 1 from XT. This is what path coupling says. It says that really you don't need to search for YT far away. Just look at the neighboring sides. So if here I have 0 red balls, 1 red ball, 2 red balls. If this is the graph of where xt could be, if xt is here, you only